Hi, I'm Sven Schepp, and I'm a grad student at the Technical University of Munich. Today, I will present SaRA, a tool that can be used to guarantee safety for human-robot coexistence and collaboration through reachability analysis. SaRA was developed together with my co-authors Jakob Thum, Stefan Liu, and Professor Matthias Althoff at the Chair of Robotics, Artificial Intelligence, and Real-Time Systems. Currently, most large-scale manufacturing relies on a combination of human personnel and robots for efficient production, where humans and robots are separated by caging and light curtains for safety purposes. This approach, however, does not enable any human-robot collaboration and only very restricted coexistence. Alternatives that utilize predictive or reactive control methods are not verified as safe according to ISO standards. Our approach eliminates these boundaries to allow humans to enter the domains of moving manipulators under guaranteed safety. The use cases for this kind of approach extend beyond industrial settings and into everyday human lives. We aim to enable widespread integration of collaborative robots in a multitude of domains by encouraging greater acceptance of robots through guaranteed operator safety. To this end, SaRA determines the entire possible space that the human can occupy in a given time frame, which we refer to as the human's reachable occupancy. This procedure is similarly performed for the manipulator. The robot provides SaRA with the time it requires to come to a full stop based on its current velocity and acceleration. By determining the human's and robot's reachable occupancy over that time frame and checking for intersections between them, we can guarantee that the robot is at rest when it is touched by the human. This procedure is in accordance with ISO definitions of speed and separation monitoring. The reachable occupancies and possible intersections can be determined in only a few microseconds due to their simple geometric representation. This allows us to compute occupancies in real time. Each body part of the human defines its own reachable occupancy in form of a capsule or ball, where balls are used for the hands, feet, and the head, while all remaining body parts are represented as capsules. In our experiments, we have used marker-based motion capture setups to determine the required Cartesian positions as shown here. However, SaRA accepts these data regardless of the means by which they were acquired, and we have previously tested our approach with light curtains, a Kinect camera, and depth sensors. Once the positions have been acquired, the occupancies are calculated based on linear motion models, and intersection checks between the robots and humans' reachable occupancies are performed at every time step. SaRA is designed as a header-only C++-based library and is itself independent of third-party software. Our architecture defines 3 layers of abstraction that allow for alterations at each level. The highest level describes the general type of obstacle we want to model, in our case, humans. Obstacles are then made up of a set of occupancies that are given a geometric representation on the final layer. This allows us to customize the obstacle definitions in great detail, for example, by introducing new geometric representations such as cylinders, polyhedra, or zonotopes. We additionally provide a customizable ROS package that can be used to visualize the results in ARVIS. We have shown that SaRA effectively performs reachability analysis and can guarantee the operator's safety during experiments in a laboratory setting. Our next goals entail tests with multiple trained operators in a manufacturing plant to evaluate SaRA's real-world performance. Since SaRA is an open source project, we encourage everyone interested to visit our GitHub page that contains the code, our manual, and descriptions of our experiments. Thank you very much for your time, and I'm looking forward to discussing SaRA with you in the upcoming interactive session.